All right, hello, and welcome to Office Hours. I apologize for being 5 minutes late. My 2-year-old took a little longer to get into bed than normal this evening, but I'm here, and I am ready to rock if you are. Kate, I see you have a couple questions. I'm logging into my textbook, but I'm also logging in to Canvas as well, so I can answer that question about exercise 8. There we go. All right. Okay. So popping into lab. Thank you for your patience and understanding. I totally appreciate it. All right, let's see. Later. All right, exercise 8. Okay. Oops. All right, let's see. Yes, Eric, I totally can. Okay. So let's see. Calculate the molality of solution of an unknown element in carbon disulfide. Okay, so Kate, first off, okay. So these questions are related. Whoops. Oh, there we go. First off, in question 1, where it says an element dissolved and then ... There's the rest of the problem. The fact that we're dealing with an element means that our Van Hoff factor is going to be equal to 1. You only have to worry about Van Hoff factors that are greater than 1 when you're dealing with ionic compounds or strong acids. Strong acids will also have Van Hoff factors that are greater than 1. Ionic compounds will separate into multiple ions in solution, but if you're dealing with an element or a covalent compound, your Van Hoff factor will be 1. And this is also where that explanation will also answer your question about C4H10O. This guy is a covalent compound. And covalent compounds don't ionize because they're not ionic. So the Van Hoff factor will also be 1. Again, acids are a special type of covalent compound that do ionize, but other than that, anytime you're dealing with a covalent compound, your Van Hoff factor will be 1. Okay, and let's see. You also looks like you have a question about number 3. Kate, you're totally... Let's see. Let me make a note of this. All right, that was question number 3, I believe. Let's see, because they're connected. Okay. Let me edit. Yes. Yeah, totally. Yeah, okay, based on the numbers that you're given, the answer should have 2 sig figs. And that was an error in the teacher's solution manual. Go ahead and roll with the answers for 3 and 4 that have 3 sig figs. And that'll get you to the correct place. Because as you can see in both of them, 3 sig figs are not an option. Totally. Okay, and let's see. You also had a... Oh! Do I not have Chapter 12? I guess I don't have Chapter 12 homework problems assigned. What I would do is, if you're looking for Chapter 12 practice, let's see. I would look at, basically just the freezing point depression, boiling point elevation problems. Let me take a look. I'm just glancing at them. Oh, that's cumulative. So it looks like the freezing point depression, boiling point elevation problems are number 77 through 98. But honestly, Exercise 8, I would say, is the best Chapter 12 practice, because there's also points associated with it. But if you have finished exercise 8 and you're looking for additional practice, then any one of these problems from this section. And Kate, you're right. I didn't cover how to do every single type of problem in here. I covered how to find a molecular weight, how to calculate what I think is a freezing point for a solution. But with the stuff we talked about in lecture, you'll have enough information to attempt to solve these problems. Some of them are harder than others, but all of the information is there. The rest of it is just problem solving. Yeah. Totally. And actually, the problem types that I didn't do, like exactly that problem type, attempting those is actually the best way to test your comprehension of the material, because you haven't seen the pattern of how to solve that problem type yet. So it's testing, do you understand how all these pieces fit together? All right, here, let me pull. Sorry, I'm partially through pulling up the packet. Okay. So consider the redox reaction between BrO3, this is the bromate ion, and bromide to produce bromine under basic conditions. Balance this reaction using the half reaction method. Okay, so the reaction that we're being asked to balance is, here, hang on, this is packet 2. This is problem 1A. All right, so we need to balance this reaction using the half reaction method. So it's a reaction of bromate with bromide to produce bromine. All right. Now, so step number one in the half reaction method is we need to break this into two half reactions. The first, sorry, hang on. This is under basic conditions. So the two half reactions that we need to balance are the reaction of bromide going to bromine and the reaction of bromate going to bromine. So these are the two half reactions we have to balance. If you're wondering, how does that even work? The answer is, you'll notice that there are two bromine atoms in a molecule of bromine, and one comes from here and one comes from here. So both of these reactants are funneling into the same product, and so the two half reactions need to have bromine, Br2, that product, as the product for both of them. So that's why that's there. We're going to go ahead and start with the bromide half reaction, then we'll come back and do bromate, then we'll combine the two together. So first off, we need to make sure that our atoms are balanced. And right now we have two bromines on the reactant side, one bromine on the product side. And so to get the same number of bromines, we need to multiply bromide by 2. So we've got bromide multiplied by 2. And now we need to balance our charges. And when you look at the charge on each side of this reaction, we have a total charge of -2. On the reactant side, we have a charge of 0 on the product side. All right. Now, to balance charge, the only thing we can add are electrons. So we can only make a side more negative. So we need to add 2 electrons to our product side so that our total charges are balanced, right? So that we have 0 minus 2, which is equal to -2. So this is the balanced bromide half reaction. Now let's take a look at bromate. Oops. There we go. Step number 1, we need to balance our atom counts. And if we look, we have bromine. Oops. Don't want that in red. We have bromine and oxygen on the reactant side. We have 1 bromine, 3 oxygen. But we only have bromine on the product side, right? We don't have any oxygen to begin with. So first things first, we got to balance our bromine. So we multiply bromate by 2. This balances our bromine, but increases oxygen, right? Now, the way you, oh wait, hang on, put that in the wrong layer. There we go. So the way you balance oxygen, you'll recall, when you're balancing using the half reaction method, is you do so by adding water molecules. These reactions happen in aqueous solution, so you have water molecules floating around. They may or may not be involved in the reaction. In this case, they are, because we need 6 water molecules, to balance our oxygen. So now we have 6 oxygen atoms. The problem is, by balancing our oxygen atoms, we introduce 12 hydrogens to the sorry, hang on. Put this on the wrong slide again. We had 12 hydrogens to the product side, and there are no hydrogens on the reactant side. Now, we're under basic conditions, but the way you balance your atoms is you pretend that you're under acidic conditions, right? So we're going to add 12 hydronium ions to the reactant side. And now our atoms are balanced. All right? Our atoms are balanced, but we have a problem. And the problem is you cannot have hydronium ions under basic conditions. So the way that you balance your, the way that you switch from acidic conditions to basic conditions is you add 12 molecules of hydroxide to both sides of this reaction. And here's why. This works because one hydronium ion reacts with one hydroxide ion to produce one water molecule. That's a neutralization. All right. And here we have 12 hydroxides combining with 12 hydrogens. So that will create 12 water molecules plus 2 bromate ions producing, sorry, we got to remember that charge, producing 1 bromine molecule plus 6 water molecules plus 12 hydroxide ions. All right. Now we've gotten rid of the acid. We're under basic conditions, right? Which means we've got hydroxide in the mix. Now our atoms are balanced. I'm going to do one additional thing. You may notice that we have 6 water molecules on the product side and 12 water molecules on the reactant side. I'm going to go ahead and cancel. So our bromate half reaction with balanced atoms will be 6 H2O molecules plus 2 bromate ions producing 1 bromine molecule and 12 hydroxide ions. That's our balanced atom situation. We still, however, need to balance our charges for the bromate half reaction. So let me just rewrite it up here. 6 water molecules plus 2 bromate ions producing, here we go, 1 bromine molecule and 12 hydroxide ions. Here, hang on one second. I think my wife's on the phone, and I'm picking her up on my mic. Hang on one second. I'm just going to give her the heads up. Alrighty. Okay. So now we have to balance our charges. Let's take a look at this. So our total charge on our reactant side is -2 because we've got 2 bromate ions. Our total charge on our product side is -12 because we have 12 hydroxide ions. All right. Now these need to be equal, and we can only add electrons, right? We can only add negative charges. So we're going to need to include 10 electrons on the reactant side so that we get 2 minus 10 equals -12. So here, this is our bromate half reaction with balanced atoms and balanced charges. All right. Now let's bring in our bromide half reaction. Because once both the atoms and charges are balanced, for both half reactions, we need to balance our electrons. And you'll notice that we have the bromide half reaction, we're producing 2 electrons. In the bromate half reaction, we are consuming 10. And we need to make sure that the number of electrons produced is equal to the number of electrons consumed. All right, so to do that, we need to balance, we need to multiply our entire bromide half reaction by 5. That way we get, 10 bromide ions producing 5 bromine molecules plus 10 electrons. All right, and now that the number of electrons are equal in each half reaction, we're ready to recombine these and get our new balanced chemical equation. So let me just rewrite this here. 10 bromides going to 5 bromines plus 10 electrons. All right, now we need to add these together. You'll notice that we have 10 electrons on the reactant side and product side, so these cancel. You'll also notice that we have 5 bromine molecules plus 1 bromine molecule. So these, because they're both on the product side, will actually add together. So we get 6 molecules of water plus 2 bromate ions plus 10 bromide ions, producing 6 bromine ions plus 12 hydroxide ions. Now, we're almost done, but we're not quite. We're almost done, but we're not quite. A balanced chemical equation has the simplest whole number ratio of stoichiometric coefficients, and you'll notice here that if you look at all the stoichiometric coefficients, there is a common factor of 2. So once you factor that out, you'll get the balanced chemical equation: 3 molecules of water plus 1 bromate ion plus 5 bromide ions produce 3 bromine ions plus 6 hydroxide ions. All right, and that is the balanced chemical equation. And that's not just the balanced chemical equation, that is how you balance this equation using the half reaction method. Yes, Eric, it totally was a doozy. Yes, Kate, that is. Oh. Kate, that's almost exactly it. But you also have to multiply by 100 because that's what makes it a percent. So percent error is always the absolute value of the correct minus the measured. Yeah. Over the correct times 100. And that last part is what makes it a percentage. Of course. Oh. Thank you, Kate. Eric, there are, so next week is finals week. And classes are not held. Oops. During finals. I will be, like I said earlier in lecture, I'm almost done. I'm almost done writing the final exam, so I will be uploading information on the final, the content, what's on it, the percentages within the next 2 days. I haven't set the window for when it opens and closes yet, but I'm planning on putting it towards the end of finals week just to give everybody as much time to study as possible. So I'm not going to slap you guys with like a Monday final or whatnot. It's going to be near the end. Kate, great question. Kate, look for an update in our lab classes Canvas page. I'm going to be posting some information on experiments 11 and 12 soon, probably later tonight or tomorrow morning. I'm actually working on an announcement for lecture, and then I've got a couple things to post about in lab. But don't totally don't stress. I'm not going to slam you guys with a ton of work late in the game. I'm kind of working out what my solution is going to be for labs 11 and 12, but I will be posting about that soon. Again, at the very latest tomorrow, I'll be posting. Dude, Kate, it is absolutely my pleasure. It really has been. I believe it or not, the reason why I do this job is because I love teaching, and I think that office hours are the closest thing that we've had in this whole distance education experience. The closest thing we've had to that in-person, in-class connection, and I miss having that with students, and I miss sharing that with all of you. And I think this is as close as we get. And so this is as good as it gets, in my opinion, because we're working together, we're problem solving, we're in dialogue. It's not just me talking into a microphone. There's back and forth. And anyways, thank you you've been an awesome, you've been a pleasure to have in the class. Always excellent contributions, asking great questions. I hope you have an awesome night as well. Oh. Hey there, Logan. I'm so sorry. I just now saw your comments. I hope I didn't keep you waiting too long. Okay, let me see. So 18 milliliters of sulfuric acid is titrated with 2.5 molar sodium hydroxide. The initial volume of the burette was 0.48. Final reading, 22.84. What is the molarity of the sulfuric acid analyte? Okay, awesome question. So here's the thing with any titration reaction or experiment, because that's what this is. We're determining the concentration of an unknown, the molarity of a solution of sulfuric acid. We are always going to need a balanced chemical equation. And so we have the reaction between sulfuric acid and sodium hydroxide. And the products of this reaction, so this is an acid-base neutralization. So our products here are going to be water and a salt. Specifically, the salt that's formed in this reaction is formed from the metal cation and what's left over of the acid after it dumps all of its protons. So after sulfuric acid dumps both its protons, you'll have a sulfate ion left over. And the metal cation here is sodium. So this produces sodium sulfate is the salt. All right. Now we need to balance this equation before we can solve this problem. And so let's go ahead and take a look. We have hydrogen, sulfur, oxygen, and sodium on both sides of this equation. So we have on the reactant side 2 moles of hydrogen, 2 hydrogen atoms from sulfuric acid plus 1 from sodium hydroxide. We have 1 sulfur atom, 4 oxygen atoms, and 1 sodium atom. On the product side, we have 2 hydrogens, 1 sulfur, 1 oxygen from water, plus 4 from sodium sulfate, and 2 sodiums. Now, you want to go for the atoms that are the easiest, right? Most straightforward. And one that looks fairly straightforward to balance is sodium. We have 2 sodiums on our product side, only 1 on our reactant side, so we need to multiply sodium hydroxide by 2. Oops, I messed up my oxygen over here. It's 4 from sulfuric acid plus 1 from sodium hydroxide. Now, when I multiply sodium hydroxide by 2, I increase my amount of hydrogen, oxygen, and sodium. So now I have 2 plus 2 hydrogens, right? 2 from sulfuric acid, 2 from sodium hydroxide. I have 4 plus 2 oxygens, and I have 2 atoms of sodium. So sodium is balanced. Let's go ahead and take a look at what to do next. Again, go for the easiest stuff. Oxygen still looks fairly difficult. I don't know how many times 5 goes into 6, but hydrogen seems pretty straightforward. I do know how many times 2 goes into 4, and that is twice. So I'm going to multiply water by 2. This doubles my hydrogen and changes my oxygen count. Now I have 2 plus 4 oxygen atoms, and I have 4 hydrogen atoms. And that actually balances everything in one foul swoop. So this is my balanced chemical equation. And I'm going to use this chemical equation to solve this titration problem. All right. Before I even line up what I'm trying to find, what I'm given. I start by balancing the neutralization reaction because I know I'm going to need that to solve this problem. All right, now that we have that in hand, let's identify what we're trying to find, then look at what we're given. So we want to find, they ask us right there at the end of the problem, what is the molarity of sulfuric acid? So we want to know the molarity of H2so4. And molarity has an equation, so I'm going to write that out. Molarity is equal to moles of H2so4, whoops, not H2O, divided by the liters. All right, so these are the two things we need. We need our volume in liters. We need our moles of sulfuric acid. Looking at what we're given, we are given a volume of sulfuric acid, right? 18.00 milliliters of H2so4. All right, that is just one unit conversion away from our denominator. So we have basically what goes in our denominator. We still got to convert milliliters to liters, but we're given a volume, so that's nice. And then we are given a molarity, 0.205. We're given a molarity of sodium hydroxide. All right, that's interesting. And then we're given an initial burette reading of 0.48 milliliters and a final burette reading of 22.84 milliliters. These together, this initial and final burette reading, will give us the milliliters of sodium hydroxide that was used in this reaction. And anytime you're given a volume and a molarity of the same thing, you can use this to find moles. Now you'll notice that this quantity in moles is not this quantity in moles. We can use our molarity of sodium hydroxide and our volume of sodium hydroxide to find moles of sodium hydroxide, but what we need moles of sulfuric acid, and that is where this balanced chemical equation comes in. We can use our balanced chemical equation to convert from moles of sodium hydroxide to moles of sulfuric acid, and that is exactly what we're going to do. That's how we're going to get our numerator. So let's start doing some algebraic work here. So first, we need to know the volume of sodium hydroxide. And to find the volume of sodium hydroxide, we need to subtract our final volume, which is 22, right? Yeah, 22.84. And subtract our initial volume, 0.48 milliliters. 0.48 comes out to be 22.36 milliliters. You'll notice our sig figs are totally fine. The last sig fig in both of these numbers is in the second decimal place. And we're subtracting, so our answer must have its last sig fig in that decimal place, and it does. We're going to need this volume in liters, so let's go ahead and do that unit conversion. There are 1,000 milliliters in a liter. Milliliters cancel. giving us a volume of 0.02236 liters. Now, the reason why this is important is because we have our volume of sodium hydroxide, 0.205, and this is moles of NaOH per liter. And we can multiply this by our volume in liters so that liters cancel out and we're left with moles of sodium hydroxide. Now, we're not ultimately interested in moles of sodium hydroxide. We want to convert this to moles of sulfuric acid. And that unit conversion is right here. It is a 1 to 2. 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. So moles of sodium hydroxide cancel. And now we can crunch these numbers to find our moles of sulfuric acid. So we have 0.205 times 0.02236 divided by 2. Giving us 0.0022919 moles of H2so4. Sig figs here, we're limited by our molarity, which only has 3. I'm going to wait around to the end, but I'm putting those lines there to remind myself that I have 3 sig figs. All right, before we can calculate our molarity, we have our moles of sulfuric acid. We need to convert our volume of sulfuric acid from milliliters to liters. So we have 18.00 milliliters of sulfuric acid that we need to convert to liters. So there's 1,000 milliliters in 1 liter. Milliliters cancel. So our volume is 0.01800 liters. Now we're ready to calculate our molarity. Because our molarity is, we take our moles, 0.0022919 moles of sulfuric acid. And again, this number only has 3 sig figs. We divide by our volume in liters, 0.01800 liters. And this comes out to be 0.127327778. It's 1, 2, 3. All right. And so this 3 is going to round down. So our final answer is our solution of sulfuric acid has a molarity of 0.127. And that is our answer. Yeah. Totally. Logan, that is a totally solid strategy to go about. Let me know if I'm moving too fast, or if you want to see me kind of break down and expand upon like any of the particular steps. I'm totally down. You let me know what you need, and I will do my best to meet you there. Totally. All right, let's get into this. All right, you'll actually see with this problem some interesting similarities to the problem we just did. Of course, there's its own. This one will have its own twist. All right, so we have 0.4955 grams of a monoprotic acid titrated with 0.10000 molar sodium hydroxide solution. The initial volume of the burette reads 0.5 milliliters. The final reading on the burette is 37.5. What is the molecular weight of the analyte? Okay, so we've got a couple things. First, this is another titration problem. And the thing that I told you last time 100% holds true for this one. The first thing you need to do is write a balanced chemical equation. What makes this one a little tricky is it doesn't tell us what our acid is. It just says a monoprotic acid reacts with sodium hydroxide. All right, now how are we going to balance a chemical equation if we don't know the acid's identity? And here's how you do that. A monoprotic acid, this word monoprotic literally means 1H. So that means that our monoprotic acid will have one hydrogen, that's acidic, and the rest of the molecule. All right, this is going to react. Now, when this reacts, when it gets stripped of its hydrogen, an acid is a proton donor, right? So it loses H+, and that means that it has a negative charge left over. So this HA is going to become an A-. All right, so our balanced chemical equation then is a reaction between HA and NaOH. Our products, for every acid-base neutralization, the products are always H2O and a salt. And that salt is formed from the metal cation from the hydroxide and whatever's left over after the acid finishes reacting. In this case, A-. We don't know what it is, but we do know it'll have a charge of -1, and that means that it combines with our cation, which has a +1 charge, to make NaA. All right, that is the chemical equation. And you'll notice when you go to balance this chemical equation, we have Ha, whatever that is, sodium and oxygen on both sides of this equation. On the reactant side, we have 1 + 1 hydrogen atoms, 1 A chunk, 1 sodium, and 1 oxygen. On the product side, we have 2 hydrogens, 1 A, 1 sodium, 1 oxygen. So this thing is already balanced, all right? It's already balanced, and the importance there is we have a 1-to-1 ratio between sodium and our monoprotic acid, HA. All right, that is what is of critical importance to solving the titration problem. Here, hang on 1 second. Okay. All right, now, with that in mind, let's look and unpack in this problem what we're trying to find, what we're given, and how we're going to get from point A to point B. We are trying to find the molecular weight of the analyte, and that is the molecular weight of HA. All right, whatever's in the burette is your titrant. Whatever the other thing, the thing in the Erlenmeyer is the analyte. So HA is our analyte, and molecular weight has an equation, so we should write it out. The molecular weight is equal to the grams of the analyte divided by the moles of the analyte. So if we know the mass in grams and the moles, we divide one by the other. That'll give us the molecular weight. Let's look at what we're given. The first thing we're given in this problem is the numerator of our equation for molecular weight. We're given the mass of our monoprotic acid. All right, so we have this. We know the grams of HA. Next, we're given the molarity, 0.1000 molar sodium hydroxide, and then we're given an initial and a final burette reading. Our initial burette reading is 0.50 milliliters. Our final burette reading is 37.50 milliliters. So these two together will give us milliliters of sodium hydroxide combined with the molarity can give us moles of sodium hydroxide, and that is where we will use our balanced chemical equation to find moles of HA. All right, so it's a very similar pattern as the previous problem. We're just finding a slightly different thing. We're finding a molecular weight instead of a molarity. But the thing that those two have in common is you need moles to find molarity. You also need moles to find molecular weight. And that is why they're both titration problems, because they're both involved in finding moles. So let's go ahead and do some algebra. So first off, we need to find our volume of sodium hydroxide. And we can find this by subtracting our final burette reading of 37.5 milliliters minus our initial burette reading of 0.50 milliliters. Now, when you punch this into your calculator tells you that the answer is 37. It's the correct value, but we have to have the same precision as our least precise number because we're doing subtraction. Both of these numbers are precise to the second decimal place, so we need an answer that is precise to the second decimal place, that has its last significant digit in that second decimal place. So we add a 0.00 onto the end of our 37. Next, we need to convert from milliliters to liters if we're going to use our molarity to find the moles of sodium hydroxide. So 37 milliliters is equal to 0.03700 liters. All right. Now, we know our molarity of sodium hydroxide. Sorry, once you have the volume of sodium hydroxide, we can find our moles. The way you do is you take your molarity, which is 0.1000, and molarity has units of moles, NaOH, per liter. If you multiply this by your volume in liters, you'll notice that your volumes cancel and you're left with moles of sodium hydroxide. Just like the last problem. We're not ultimately interested in moles of sodium hydroxide. We actually want to find the moles of our acid, HA. And our balanced chemical equation tells us that we have a 1-to-1 ratio here. 1 mole of acid reacts with 1 mole of sodium hydroxide. So we're going to crunch these numbers. And 0.1000 times 0.03700 is 0.0037. But for both of these, you'll notice there are 4 sig figs. So we need 4 sig figs in our answer. 0.003700 moles of monoprotic acid react. Now, we're ready to calculate our molecular weight, because molecular weight is mass, 4955 grams of monoprotic acid, divided by moles, 0.003700 moles of monoprotic acid. So we go let me clear this, 0.4955 divided by 0.003700. And my calculator is telling me the answer is 133.918919. We can keep 4 sig figs. Both our numerator and denominator have 4. This one will round down. So our molecular weight of our monoprotic acid is 133.9 grams per mole. And that is that titration problem. Lauren. I absolutely can do examples in exercise 6 similar to those. Yeah. Logan, that sounds like an awesome plan. Okay, Lauren, let me pull up exercise 6, and we will get to work. Okay, hang on. Okay, Lane. Sorry, Lauren, I'm trying to look up so hang on, it might be back. Just waiting to see if testing one more thing. All right, good. We're good. Awesome. We are once again live. That has never happened to me before. So Lauren, question. Oh, let's see. There we go. This does not look like your number one problem. All right. Oh. Okay, awesome. Awesome. I will be able to find it now. There we go. Okay. Give me 1 sec. I'll pull it up. So you have... okay. All right, let's... Yeah, so the order in which I created the problems, there was something messed up in Canvas. So, for example, that problem that you're doing is my problem. I originally had that one written as problem number 8, but it's showing up as number one for you, and so there's a little kind of snafu in Canvas where it didn't order the problems in the order that I created them when it sent it to an assignment. And I've, since the creation of exercise 6, I figured out why that is. But because exercise 6 was already live, I couldn't, the Canvas doesn't let you edit live assignments. That way it's the same for everybody, no matter when they do it. Which I totally get, which is fair. Okay, so for this is your number one. So let me pull this over here. Totally, Logan. After I do this one, I'll hit that one up next, and then we'll go back and forth for a little bit. Okay, so for the following reaction has a change in enthalpy, and they give us the reaction of N2O4 decomposing into 2 N2O. This reaction has a change in enthalpy, delta H, of 58.2 kilojoules per mole. And then they ask us to determine the moles of dinitrogen monoxide produced, and this is where I'm going to change it around slightly. I'm just going to alter the numbers. If 588 kilojoules are absorbed, all right, so solving this problem 100% hinges on how you handle the delta H for your reaction. Now, when you have a positive delta H, that means energy is absorbed, right? Energy is absorbed. That means that energy, you treat energy like a reactant. All right? Energy is a reactant in this reaction. So you take, to solve this problem, you need to incorporate your change in enthalpy into your balanced chemical equation. And because it's a reactant, you write it on the reactant side. 58.2 kilojoules of energy reacts with 1 mole of N2O4 to produce 2 moles of N2. All right? And once it's in the balanced chemical equation, you can do stoichiometry. So you're given that 588 kilojoules of energy are absorbed in this process. We want to know how many moles of N2 are produced. So we need a unit conversion to convert between kilojoules of energy and moles of N2O. And that unit conversion is right here. For every 2 moles of N2O produced, 58.2 kilojoules of energy react. All right? So kilojoules cancel kilojoules. We're left with moles, which is great because that's what we are after. And so now we crunch our numbers. 588 times 2 divided by 58.2 is 20.206186. Based on the numbers we have to work with, we're limited to, in this problem, we're limited to 3 sig figs. Oh, that's weird. 2020 showed up in this number. 0 rounds down, so our final answer is 20.2 moles of N2O are produced. Now, that's not the answer to the problem as it appears on the exercise because I changed the numbers, but this is how you solve it. Awesome. And Lauren, I will totally hit up your other questions as well, but I'm going to do Logan's next, and we're just going to kind of alternate back and forth. So hang tight. Think of the questions you asked me. Think of which one you want me to hit up next, and I'll do that after answering Logan's question, which is okay. This is a excellent example. Oops. Awesome. Thank you for being flexible. So Logan's question is, how much water do you need to add to the concentrated solution to prepare um 5.00 liters of 0.250 molar hydrochloric acid. All right. Logan, quick question. So we need one more piece of information to solve this problem. Logan, what is the concentration of the concentrated solution? Without that information, this problem can't actually be solved. But if we know what that is, then we can. Because this is this type of problem is a dilution. And the dilution equation looks like this. Its initial molarity times initial volume is equal to final molarity. I'm sorry, that should be final. It's equal to final molarity. Oh, sorry, that's an ugly M. Let's try this again. Initial molarity times initial volume is equal to final molarity times final volume. And you'll notice that in this problem, we have our final volume and our final molarity. Oops, sorry, not our final molarity. So we've got these two We're being asked about volume, but we need... So we're being asked about... Oh, no, sorry. Yeah, okay, right. Huh. Review packet 5. Okay, let me pull it up real quick. Okay. Yeah. And so, okay, I'm looking at the problem. So we're told that. Okay, so we're given. So in this problem earlier, it stated that we have 11.37 molar hydrochloric acid, and we're told it's used to prepare 5 liters of 0.25 molar hydrochloric acid. So the way this problem would be framed is how much water do you need to add to to 11.37 molar HCl to prepare 5.00 liters of 0.250 molar HCl. All right, so here's the deal. You'll notice that right here, oops. This is our M1. This is our M2. And this is our V2. All right, because the equation is initial molarity times initial volume is equal to final molarity times final volume. So the initial, we're given 3 out of 4 of these quantities. And so we can solve. We divide both sides by initial molarity. They cancel out of the right side of our equation. So we get initial volume is equal to M2 times V2 over M1. Final molarity, 0.250 molar. Final volume, 5.00 liters. Initial molarity, 11.37 molar. You'll notice that molarity cancels. And so we can crunch our numbers. 0.250 times 5 divided by 11.37 gives us an initial volume of 0.10, let's see, 3 sig figs, 99. But when we round to 3 sig figs, this 9 rounds up, which is going to bump that 9 up to a 10. So this will be 0.110 liters. All right. Now here's the deal. So we just found V1 is 0.110 liters. This
is the volume. This is the initial volume of 11.37 molar HCl. But you'll notice that that's not what this problem asked us to find. This problem didn't ask us to find the initial volume of HCl. It actually asked us, how much water do you need to add to? How much water do you need to add to the 11.37 molar HCl? So the water that you need to add to this will be the difference between your final volume and that initial volume you start with. So we actually need to subtract. We know what our final volume is. We just found where we started. The amount of water we add is going to be 5 liters minus 0.110. So we need to add 4.89 liters to the 11.37 molar HCl. Logan, that is how you handle that problem. Definitely on the trickier side of things, because it's not as straightforward as asking for the initial volume. Oh, did I ask for the same thing twice? Oh, that was part B. How much do you need to add? Part A is asking how much concentrated hydrochloric acid is needed to prepare it. So part A is asking for V1. Part B of this problem is asking how much water you need to add to it. All right, determine oops. There we go. Okay, awesome. All right, let's see. All right, I got it dialed in. Okay, so let's take a look at this beast of a problem. All right, so we're back to exercise 6. Okay, so we want to find the delta H for this reaction. All right, so we are after. Wait, hang on. Let me just make sure I got the right one. Yes. Okay. Good. So we want to find the delta H for this reaction. Whoops, not in blue. So we've got 2 moles of magnesium oxide reacting with 4 moles. Oh, sorry, not of aqueous. Of gaseous HCl. Producing 2 moles of magnesium chloride. Oh, which is not aqueous, which is solid. And 2 moles of liquid water. So we want to find the delta H for this reaction. Now let's look at the reactions that we are given. First, we're given solid magnesium plus 2 moles of HCl gas producing magnesium chloride, which is a solid, and H2 gas, and this reaction has a delta H of, okay, and Lauren, I'm going to just alter these numbers so that I won't be giving away the answer. But this, so I'm going to change these delta H's. This will be 342.0 kilojoules per mole. Next, we have 2 moles of solid magnesium reacting with O2 gas to produce 2 moles of magnesium oxide, which is a solid, and this has a delta H of negative 985.2 kilojoules per mole. Finally, we have 2 moles of water, liquid water, producing 2 moles of hydrogen gas and 1 mole of oxygen gas. And this is a delta H of 394.6 kilojoules per mole. All right, now you so to solve this problem, we are going to need to manipulate these chemical equations into So the goal is we're going to manipulate these either by multiplying them, by flipping them, and then at the end we're going to add them all together. And when we add all of our manipulated reactions together, we want these 4 members of our goal reaction to be present, and then we want every species that isn't in our goal reaction to cancel. So, so just by way of a brief reminder, so these are just the rules of the game we're playing. If you have a reaction A plus B produces C, we'll call this delta H1. If you multiply everything in your reaction by the same number, your new delta H, which I'll call delta H2, will be equal to your first delta H multiplied by that number as well. So that's kind of rule number 1. Rule number 2 that we're going to use, again, just by way of review, is if you have a reaction A plus B produces C, and this is delta H1, if you take your reaction and you flip it around where you say C produces A plus B, you swap your reactants and products, your new delta H, delta H2, is equal to your old delta H multiplied by -1. All right, so you can flip any reaction around. You just multiply your delta H by -1. The last rule is you can add two reactions together. So if you have A plus B produces C, say this is delta H1, and then you have a second reaction where C decomposes into 2 moles of D. We'll say that this is a delta H of 2. You can add these reactions together to get a new reaction. You'll notice that C is a reactant and a product, so it cancels. Our new reaction when you add these together is A plus B produces 2D. And our new delta H, we'll call this delta H3, is equal to the sum of the two delta H's for the reactions that we added together. All right, so these are the rules of the game that we're going to use. And the last step of all of these problems will be this third rule right here, where you take your reactions, add them together, and you want the stuff that's not in your goal reaction to cancel, like our C's, and then you want the stuff that is in your goal reaction to stay. All right, with that in mind, let's take a look at what we have to work with here. One thing you'll notice is, so we have magnesium oxide, HCl, magnesium chloride, and H2O. Those are all the things in our goal reaction. We want to find those in the reactions given and then manipulate them into showing up at the correct places and the correct time. So, for example, you'll notice that we have 4 moles of HCl, and in this first reaction, HCl is on the reactant side, which is good. Our goal reaction has HCl on the reactant side, but we have 2 moles of it in this reaction, where we want 4 moles of HCl in our goal reaction. So we need to take this reaction here and multiply everything in it by 2. When we do that, we get 2 moles of solid magnesium plus 4 moles of HCl gas produces 2 moles of magnesium chloride solid plus 2 moles of H2 gas. And the delta H here is the old delta H multiplied by 2. So we take 342 times 2. Sorry, negative 342. So this will come out to be negative 684.0 kilojoules per mole. All right. So we just manipulated that first reaction to get this new reaction. And we're going to take it and save it for later, because it is going to be one of the reactions that we add together at the end of this problem. And you can see that we have 4 moles of HCl gas on the reactant side like we want. All right? But we're not done here. We've got our 4 moles of HCl taken care of. Let's look at magnesium oxide. Now, one of the things you may notice, it jumps out to me here, is we actually do have 2 moles of magnesium oxide, which is what we want. We want 2 moles of magnesium oxide in our goal reaction. The problem here is it's on the wrong side of the equation, right? We want 2 moles of magnesium oxide on the reactant side, and in this reaction, it's on the product side. So we need to take this reaction and flip it, which multiplies our delta H by -1. So when we flip this reaction around, wait, hang on. Okay, yeah. When we flip this reaction around, we exchange our reactants and our products. So this will be 2 moles of magnesium oxide produce 2 moles of solid magnesium plus 1 mole of O2 gas. And our delta H here is our original delta H multiplied by -1. Negative times a negative is a positive, so that's 985.2 kilojoules per mole. All right, so now we can add this reaction to our list that we're going to all add up at the end of this problem. And now we have our 2 moles of solid magnesium lined up. All right, let's look. Now that we have magnesium, let's maybe figure out magnesium chloride. Magnesium chloride is, let's see, right here. And it's on the correct side. We want it as a product, but we only have 1 mole of magnesium chloride, and here we want 2 moles on the product side. So we need to take this reaction and multiply everything by 2. All right, when we do, oh wait, hang on one hot second. Sorry, oh, that looks gross. We've actually already done this. We already have two moles of magnesium chloride on the product side. It came with the first reaction. So we have actually taken care of magnesium chloride. The last thing we need to place is water. So let's take a look with fresh eyes. We need water. And we need 2 moles of water, which we have, but we need it on the product side, and in this reaction, water is on the reactant side. So we need to flip this reaction. When we flip it, we get 2 moles of H2 gas plus 1 mole of O2 gas produces 2 moles of H2O liquid. And here we flip our delta H, multiplying it by -1. All right, and now we have a reaction that is good to go. You'll notice that we have oops, 2 moles of water on the product side of the reaction. So all that works out. The question is, does all of the other stuff cancel? And one of the things you'll notice is 2 moles of solid magnesium are on both the reactants and products side. 2 moles of H2 gas on both the reactants and product side, so they cancel. And 1 mole of O2 gas, so on both the products and reactants side. So we're left with, the only 2 reactants we're left with is 2 moles of magnesium oxide, solid magnesium oxide, plus 4 moles of HCl gas, producing 2 moles of magnesium chloride, which is a solid, plus 2 moles of H2O liquid. That is our goal reaction. To calculate the delta H for this reaction, we just need to add these 3 delta H's together. So we have negative 684 plus 985.2 minus 394.6. So this comes out to be, my calculator's telling me that my answer is negative 93.4, which of course is different than the answer on the exercise itself. When you look at sig figs, all 3 of these numbers are precise to the first decimal place. The answer my calculator gave me is precise to the first decimal place as well. So I don't need to round or add any zeros or anything because my last sig fig is in the first decimal place. And that is the answer using the numbers that I'm using here. All right, let's see. Oh. All right, okay, let's take a look. All right, let's see. A 1.5 liter sample of water has an initial temperature of 19 degrees. Okay. All right. So we have a 1.5 liter, or 1.5 liters of water. Has an initial temperature of 19 degrees Celsius. What is our final temperature if it absorbs 62.8 kilojoules of energy, and they give us a specific heat of water of 4.184 joules per gram degrees C. All right, so anytime you are given a problem that has specific heat in it, you will most likely have to use the equation Q equals MCAT, because that's the only thing really that has specific heat in it. You'll notice that, and part of Q equals MCAT is change in temperature is equal to final temperature minus initial temperature. We are being asked to find T2, right? This is what we're after. We can find T2 if we have T1, and we do. T1. The second thing we need is change in temperature. And you'll notice change in temperature is in Q equals MCAT. We can find delta T if we know the mass and the thermal energy, change in thermal energy. Turns out we do know the change in thermal energy, but we don't quite have the mass. We have something close to it. All right? We don't have the mass, but we do know the volume of H2O. The quantity that relates mass to volume is density. Density is equal to mass over volume. Now, we haven't been given a density of water in this problem. Yes, okay, totally. Lauren, you're right at where I am in this problem. But we can look it up. All right, and if you look up the density of water, there's like a ton. You may not know which one do I use. But this problem is a multiple choice for a reason. It's a multiple choice, so you don't have to enter the correct numeric value. And the density of water is always around 1.0 0 grams per milliliter. So if you're ever unsure, you can always just use 1, and that will allow you to find your mass, because you can solve by multiplying both sides by volume. Mass is equal to volume times density. Our volume is 1.5 liters. Our density is 1.00 grams per milliliter. Now, we actually have a problem here because liters and milliliters need to be the same unit. So if we convert 1.5 liters to milliliters, there are 1,000 milliliters in a liter. And so that comes out to be 1,500 milliliters. Now we can find the mass of water. So that'll be 1,500 grams. My sig figs are fine because I'm limited to 2 based on this initial volume. So now we have our mass. We can solve for our delta T, and then we can use our delta T to solve for our final volume. So first we use, oops. Q equals MCAT. We're going to divide both sides by mass and specific heat. So we isolate delta T on one side of the equation. Our change in temperature is equal to Q divided by mass times specific heat. Tatiana, I will totally hit up that question once I'm done working this one. So hang tight and we will get to it. All right. Okay. Fun times. So the amount of energy that we absorb here, 62.8 kilojoules over our mass, which we just solved for, 1,500 grams, times our specific heat, 4.184 joules per gram degree Celsius. Now here we run into a second units problem. Our specific heat capacity has a energy unit of joules, but we've been given our energy in kilojoules. These two need to be the same in order for us to plug them in. So let's convert 62.8 kilojoules to joules. 1 kilojoule is 1,000 joules. So our energy unit in our numerator, or our energy in units of joules, will be 62,800 joules. And now we're set up for all of our units to cancel. Joules cancel joules, grams cancel grams, and we can crunch our numbers. So 62,800 divided by 1,500 divided by 4.184 comes out to be 10.00633735. Units are degrees C. We're limited to Let me see here. Okay, hang on. So we're actually limited to 2 sig figs, right? Because we have 2 sig figs down here. 0 is going to round down. So the correct answer here is oh wait, this is exercise 6. I'm just making a note. So you'll notice here that that the correct answer should have 2 sig figs. It should be 10. The only way to write 10 with 2 sig figs is 1.0 times 10 degrees C. And that's not an answer. There's 10 with 3 sig figs, there's 10 with 1 sig fig. But the correct answer is impossible, so I'm going to have to give everyone full credit for this problem. So, anyways, that's fortuitous. All right, Tatiana, let me pull up packet 2. Okay. Oh, pff. Duh. Oh my gosh. I'm sorry, Lauren. So wait, hang on. So we might actually be fine. Let's solve for T2. Let's maybe solve the problem that I'm asking for, and maybe good things will happen. Okay, yes. Sorry. Let's do that. Oops. Okay. It has been a long day. Okay, so let's see here. We just found delta T, but we want to find our final temperature. Right, okay. So maybe we're fine. Who knows? We could still be messed up. But let's find out. So we want to get, sorry, this is not plus, this is minus. Delta T is T final minus initial. We need to add our initial temperature to both sides of this equation to isolate T2. So T2 is equal to delta T plus T1. Delta T we just solved for. It's 10.006 degrees Celsius, but there's only 2 sig figs here. Plus plus 19.0, that's our initial temperature, degrees C. When you add these two together, my calculator tells me that the answer is 29. Degrees Celsius. And that's actually correct because our last sig fig needs to be in the ones place. 29's last sig fig is. So that's the answer there. So I take back everything I said. Yeah, the answer is 29. Totally. Totally. All right. Okay. With that problem solved, Tatiana, I can get to your question from packet 2. This is problem 2. All right, let's see. All right, so we're told that aluminum metal, which is a solid, is mixed with hydrochloric acid to produce hydrogen gas. Help on part B. Okay. Okay, awesome. Awesome. Then I will just balance this thing really quick. Hydrogen gas and aluminum chloride. All right, so this balanced chemical equation will need six HCl's, 2 aluminums, 3 H's, and 2 aluminum chloride. So that's the balanced chemical equation. And then Tatiana, specifically, your question is on part B. Determine the molarity. So first, let me write out what we're given. We're given that we have 15.0 grams of solid aluminum. We're given that we have 1.5 molar solution of HCl, and that we use 75.00 milliliters of it. And then part B, in part B, we're asked to find the molarity of the aluminum chloride solution. All right, so we're going to do a little conceptual work first, kind of laying out the problem, then we'll get into the nitty-gritty. So first off, if we want to find molarity, we should write out the equation for molarity, because that'll tell us the pieces we need to identify. We need to find moles of aluminum chloride, right? Because molarity is moles of aluminum chloride per volume in liters. And you'll notice that that we only have one volume present. in this solution, or sorry, in this problem. And that volume is the 75 milliliters. So that'll be our denominator. All right. That's our denominator because we added 15 grams of aluminum to the solution. But the solution doesn't change when things get dissolved in it. When solid solutes get dissolved. And so that volume of HCl is going to be the volume that contains the aluminum chloride. We have to convert it to liters, of course. But that value, once converted, will be the denominator. Now the question is, how do we find the moles of aluminum chloride produced? Well, in this problem, you'll notice that we're given an initial quantity of HCl and we're given an initial quantity of aluminum. When you're given initial quantities of more than one reactant, you have to do a limiting reactant calculation because the limiting reactant determines the amount of products produced. All right, the moles of limiting reactant determine the amount of products produced, and aluminum chloride is a product. So we need to take these two initial quantities of our reactants, figure out which one is the limiting reactant. So we're going to calculate how many moles of aluminum chloride could be produced by either. Whichever one is smaller, that will determine our moles of aluminum chloride. Tatiana, that is spot on. The temperature is extra information for this part of the problem. All right, so let's do the limiting reactant calculation, starting with aluminum. So we start with 15 grams of aluminum. Step number one, we need to convert grams to moles. And the atomic mass of aluminum, it's like 26 something. Yeah, it's 26.98. So grams of aluminum cancel. Next, we want to convert from moles of aluminum to moles of aluminum chloride. And this unit conversion we get straight from the balanced chemical equation. 2 moles of aluminum produce 2 moles of aluminum chloride. And we can stop there. We don't have to go to grams because, again, we're trying to find molarity, so we actually just want to know how many moles of aluminum chloride are produced. So we have 15 divided by 26.98 times 2 divided by 2. This comes out to be 0.5967 moles of aluminum chloride. We can only keep 3 sig figs. Sean, I will check. Once I finish this problem, I'll give exam or packet 3 a check and let you know. I'm going to wait to round to the end. Well, one, I don't even know if this is the correct answer. We have to repeat this calculation for HCl, figure out how many moles that could produce. So, sorry, not 15. We have 1.5, a 1.5 molar solution of HCl. And again, molarity is moles of solute, so moles of HCl, over liters of solvent. So we need to to find our moles of HCl, we need to multiply by our volume, but converted to liters. And 75 milliliters is 0.07500 liters, and now volume cancels. Next, we need to convert from moles of HCl to moles of aluminum chloride. And again, this comes straight out of the balanced chemical equation. 6 moles of HCl produce 2 moles of aluminum chloride. Moles of HCl cancel. And we are good to crunch our numbers. 1.5 times 0.075 times 2 divided by 6 is 0.0375 moles of aluminum chloride. Here, we're limited to 2 sig figs because we have a molarity of 1.5. And this is the theoretical yield because it's smaller. It's the theoretical yield of aluminum chloride in moles, which means that this is the quantity that we want. This is the quantity that is produced, so this is the quantity that we'll use to calculate our molarity. All right, now, again, molarity is equal to moles of solute over liters of solution. We just determined that we produce 0.0375 moles of aluminum chloride in this reaction, only 2 sig figs in our numerator. And our volume, as we discussed before, is 75 milliliters, but we have to enter that value in liters to calculate molarity. So 0.0375 divided by 0.07500 gives us a molarity of 0.5 is what my calculator tells me. I need 2 sig figs though. So 0.50 molar aluminum chloride is the concentration of the solution of aluminum chloride that is produced. All right, Sean, let me take a look at packet 3 real quick. So you said it was number 5B. Well, that's 6. 5. Chemical reaction, 3.2 moles of limiting reactant, completely releasing, doing that many joules. Determine. Oh, Sean. Okay. Now that I see the problem, so Sean, because I didn't specify which unit to use. I didn't say what's the answer in joules or what's the answer in kilojoules. Either one would totally be accepted, as long as the value is correct. I'll accept it in joules or kilojoules. Lauren, I can totally do one more problem. Tatiana, I'm so glad I could help. Okay, let's see. Let's see. Okay. Ba-dum-bum-bum. Sorry. Carbod disulfide. That's a little bit of a typo there. Okay, let me get back to that exercise. An element in carbon disulfide if 4.425 grams of the element are dissolved in 100 grams, producing a boiling point of... Okay. So we're being asked to calculate the molality of an element in carbon disulfide if 4.425 grams of the element are dissolved in 100.0 grams of carbon disulfide. Producing a solution with a boiling point of 49.48 degrees Celsius. All right, there's a couple things that are missing from this problem that we need to look up. And I believe they're given actually at the... Oh, nope. Oh, not that one either. Oh, right, it's number 8. Right, so we have, let's see, we're dealing with the boiling point. So carbon disulfides, pure carbon disulfide, yeah, is 46.23 degrees Celsius and has a boiling point constant of 2.35 degrees C per moles per kilogram. All right. So, yes. Okay. Awesome. What I am going to do is again, just slightly tweak these numbers so I don't give away the answer. So I'm going to make this 52.48. I'm also going to make it 150 grams of solution. All right, so first up, as always, let's identify what we're trying to find in this problem. And we are trying to find the molality. Now, molality equals moles of solute over kilograms of solvent. But this doesn't seem like a likely way to solve this problem, because we're told that we want to calculate the molality of an unknown element. So even though we're told the mass of the element, because we don't know what the element is, we don't know its atomic mass, so we can't find its moles. Fortunately, molality shows up in another equation. The change in boiling point is equal to the Van Hoff factor times the molality times the boiling point coefficient. And so this might be a better opportunity to find our molality if we can find these three things. And the cool thing is, we have Kb, right? It's right here. We have our Van Hoff factor because we're told that this is an element, and only ions and acids break apart. So because this is an element, our Van Hoff factor is just 1. We got this guy. Now for the change in boiling point. We can actually calculate this based on the solution's boiling point and the boiling point of the solvent, because our change in boiling point is equal to the solution's boiling point minus the solvent's boiling point. So our change in boiling point is equal to 52.48 degrees C minus 46.23 degrees C. Again, I'm using my slightly different numbers, just so I don't give anything away. So 52.48 minus 46.23 gives us a change in boiling point of 6.25 degrees Celsius. Sig figs are spot on because our precision is in that second decimal place. So now that we have our change in boiling point, we can solve for the molality. We can solve for the molality if we divide both sides of this equation by our Van Hoff factor and Kb. So molality is equal to the change in boiling point 6.25 degrees C over our Van Hoff factor, which is 1, and 2.35 degrees Celsius over mole per kilogram. So 6.25 divided by 2.35, 6.25 divided by 2.35 gives us a molality of, we're keeping 3 sig figs, 2.66. You'll notice degrees, whoops, I want that to be yellow. Degrees Celsius cancel, and our units are moles. I'm going to write that in a linear fashion. Moles per kilogram. All right, and that is the molality of our unknown element in C2, CS2 carbon disulfide. Ah. Tatiana, so I did make one. Alrighty, and it is 10:03, so that'll bring our final office hours of the semester to a close. Thank you all the night owls who are still here and hanging out. Thank you to everybody who came, showed up, asked questions tonight and all semester long. I wish you absolute best of luck on the final and in all your future endeavors. Lauren, I hope you have an awesome 2021 and an excellent night tonight. Again, keep an eye out. I'll be posting about the final within the next 2 days, either tomorrow or the day after. I'm just wrapping up creating it. I'll give you all the details on which concepts are there, what the percent points are associated with the concepts, all that good stuff. And you'll take your final. We'll wrap up this semester and sail on into 2021. I think we're all looking forward to some change. So anyways, have a great night. It has been a pleasure, and I will catch